atoms, generally potential energy is for atoms, potential energy is more. For molecules, potential energy is less. More potential energy means generally these are less stable. Less stable. Less potential energy means these are generally molecules are more stable. Based on these atoms and molecules, here atoms cannot exist as independently because its energy is more or less stable. They are eagerly waiting to get the stability either by losing or gaining or sharing of energy in terms of electrons. Now here the molecules are generally formed by the combination of atoms plus atoms. It gives molecules generally. Now here the molecule energy is more, while reacting these two atoms, some amount of energy loses and it gives a molecule. This molecule energy, potential energy is less, that's why they are more stable. Your potential energy is more, that's why these are generally less stable. So while forming molecule from respective atoms, always amount of energy is released. That's why formation of molecule always an exothermic in nature. Amount of energy is released. A graph is plotted between here potential energy and reaction coordination or the bond length. This is the potential energy. And it is a bond length BL or reaction coordination. Initial, I'll take one certain state. The potential energy state is here. Amount of energy is more. Here, two atoms are farther distance, like farther distance. These two are slowly ready to combine. Atom 1 and atom 2 ready to combine, or AB ready to combine. Then its potential energy, while combining two atoms, potential energy, what happens? Decreases. From here to slowly its potential energy decreases and it forms like products, certain products. Now while combining these two atoms, your perfectly combines, your amount of energy decreases. Potential energy, this is the molecule, this is the atom. Now between there is a attractive forces exist. Between attractive forces present between two atoms A and B. Here there are farther distance, but here closer to each other. Bond length is less, shorter distance. They are very close to each other, attractive in nature. They are very close to attractive in nature means bond length is less. They are very strong in nature. They are stable. Energy, potential energy also very, very less. That's why molecules are independently exist, but atoms cannot because energy is more. They are not stable. Now above this, your negative repulsive forces are present. Repulsive forces. Repulsive forces means again they are divided and converted into atoms. So this is the zero, neutral. Above your repulsive forces, your attractive forces are present. Why these atoms are ready to lose some amount of energy means to get the stability of the atoms. So to attain the stability of atoms, these atoms while combining some amount of energy loses, molecules becomes more stable. Diagrammatically we can explain. So by using this diagrammatical explanation with the help of Valency bond theory, I will explain once again attractive and repulsive forces between what type of molecules, what type of particles, attractive and repulsive forces exist. Okay. Now here atoms and atoms combines, it gives a molecule. While combining these two atoms, some amount of energy loses. While combining these two between there exists a certain attractive and repulsive forces. Between atoms and atoms, attractive and repulsive forces exist. Whenever attractive force is more than compared to the repulsive forces, then immediately it gives the molecule. Between atoms and atoms, attraction is more than combines, it gives molecule. That's why while forming molecule, attractive forces are generally more than compared to the repulsive forces. Repulsive forces are less than attractive forces. Then it gives immediately molecules. Very, very important. So while forming molecule, these atoms ready to attain stable octet electronic configuration. What is octet electronic configuration? Now here octet electronic configuration, each and every one atom try to get a stable octet electronic configuration either by losing or gaining or sharing. Now here octet electronic configuration. Easy. We know already in periodic table. In periodic table, long form of the periodic table consists of 7 periods and 18 groups. This is a simple skeleton of long form of the periodic table. In this skeleton of long form of the periodic table, here blocks, 4 blocks are present, SPDF blocks. This is the S block, this is the P block, this is the D, and this is the F block. Skeleton. In this long form of the periodic table, extremely right hand side of the periodic table contains 18th group, that is called a zero group, that is a noble gas electronic configuration, noble gases. Now there are helium, neon, argon, krypton, xenon, radon. In the periodic table, each and every one element try to get this electronic configuration either by losing or gaining. Here except helium. Helium atomic number is 2, electronic configuration is 1s2. It has duplet electronic configuration, EC. Remaining all are helium, neon atomic number is 10, like 1s2, 2s2, 2p6. In its outermost orbit, 8 electrons are there. It is ns2 and np6. Now here ns2 electron, np6 2 electrons, total 8 electrons are there. This is the octet electronic configuration. Now here the argon 18, 1s2, 2s2, 2p6. Here 3s2, 3p6, 3d is there, but there is no electrons. Now this is the outermost orbit. Here also contains 8 electrons. Argon, krypton now. Here 36. Here it is 1s2, 2s2, 2p6, 3s2, 3p6. Originally here 3d10, 4s2 and 4p6 electronic configuration. 4d, 4f are available. 36, 10 plus 10, 20, 28 and 8, 36. it is a last number. Once we can observe here 1s2, 2s2 2p6, 3s2 3p6, 4s2 4p6. Top to bottom, what happens? Size increase. Here only one energy level is there. Here are two energy levels. Here are three energy levels. Here are four energy levels. Top to bottom size increases in a period. Sorry, in a group. In a period, left to right size decreases. Now this is a last number n equal to 4 for any atom last valence shell. This is called a outermost orbit. Outermost orbit or valency shell. This is also called a ultimate shell. It is ultimate shell. Last but one, third is the main energy level, that is n minus 1 equal to 4 minus 1 equal to 3, n minus 1 value. This is called a last but one, that is called a penultimate shell. This is the last but two, that is n minus 2, that is 4 minus 2, that equal to 2. This is called a anti-penultimate shell. Anti-penultimate shell. Now this is called a inner. Now remaining all are called a inner shells. Like krypton, xenon and radon, we can write electronic configuration. Now in this first energy level and last energy level, in between these two energy level, here 2, 3 are called a core shells, core energy levels. Electrons present in the core shells are called a core electrons. Between first and last, in between energy levels are called a core shells. So in periodic table, extremely right hand side of the periodic table, here 18th group elements, 0 group are noble gases, rare gases, all the elements, arogens are cosine. So in periodic table, each and every one element try to get the stable octet except helium. Helium has a duplicate, remaining all are 8 electrons in its outermost orbit. So while forming molecules, these atoms try to get this electronic configuration either by losing or gaining. So in this losing or gaining or formation of molecule, atoms loses or gain or shares, it forms corresponding stable molecule. If it contains in its outermost orbit, each and every one atom or molecule or ion or any species, 8 electrons, such molecules obey the octet electronic configuration. Which do not contain 8 electrons in its outermost orbit, the valency shell, such molecules do not obey octet rule. That is the limitation. They are the limitations of octet electronic configuration. I will cover all these. Now here, generally, your 8 electrons or 5 electrons or 6 electrons or whatever it, from each and every one atom in its outermost orbit, how many electrons are present? Such electrons are called a valency electrons. Such a valency electrons, number of valence electrons are represented by Cosell and Lewis by using a dot method, dot structure. Very, very important this is. In objective, regularly based on this dot method, they'll ask cross or the dot method. Lewis dot structure. Which of the following is the Lewis dot structure? What is the main use? What is the main importance of Lewis dot structure? So next concept is based on this. Lewis dot method or Lewis dot structures of atoms and molecules are the species. So here, Lewis dot structures. Lewis, Kusel and Lewis dot structures. For example, here the hydrogen, lithium, sodium, potassium, rubidium, cesium, francium are the first group elements except hydrogen. Remaining all these are called alkali metals. Hydrogen electronic configuration 1s, lithium 1s2 2s1, sodium 1s2 2s2 2p6 and 3s1, potassium 1s2 2s2 2p6, 3s2 3p6 4s1 and so on. For this we'll get 5s1. For this we'll get 6s1. For this we'll get 7s1. Lewis introduced one of the most important concepts, that is Lewis dot structure, to represent the number of valence electrons with the help of a dot. Dot means like one dot indicates it contains one electron in its outermost orbit. Here two dots, nothing but two electrons are present. These two dots are separately, if we can write, they are not a paired, they are unpaired. If we can write two dots side by side, they are paired in nature. Now, for all these first group elements, in its outermost orbit, here one electron only present. That is the outermost orbit. Here helium, this is the neon electronic configuration. This is the argon electronic configuration. This is the stable nature. So for all first group elements, here inner electrons, except these inner electrons are completely paired they are. But only one electron is responsible to transfer, to donate, to share. That is only for alkali metals. So for all alkali metals, lithium Lewis dot structure is Li 1 dot, sodium 1 dot, potassium like, here the rubidium like. So the 1 dot indicates here lithium contain total 3 electrons. Out of 3 electrons, 2 are completely paired, that is inner orbit, do not involve in a chemical bonding. Only 1 electron only participate, that is a valency electron. That valency electron is denoted by a dot, or we can use a cross. That's why Lewis dot structure is this. For second group, like beryllium, magnesium, calcium, strontium, barium, radium, second group elements, its electronic configuration is 1s2 2s2, like here 1s2 2s2 2p6 3s2, here calcium 1s2 2s2 2p6 3s2 3p6 and 4s2, this is, and so on, 5s2, here 6s2, 7s2 and so on. Once we can observe, this is completely paired stable octet argon electronic configuration. This is neon electronic configuration. This is the helium stable. That's why this we can write helium 2s2. Outermost orbit is this. That is in box method we can write here 2 electrons. They are paired. That's why we can write a beryllium 2 dots side by side. Not only beryllium, all these alkali metals, alkaline earth metals, second group elements, Lewis dot structure is like this. We can take metal here. M is beryllium, magnesium, calcium, strontium, barium and radium. We can write for this M 2 dots like. For alkali metals, Metal M is equals to lithium, sodium, potassium, rubidium and cesium. Francium, a radioactive element. We can write for this M1 dot. This is Lewis dot structure for alkali metals. Like in the long form of the periodic table, each and every one element, number of valency electrons are represented by dot by Lewis. That's why it is called a Lewis dot structure. This is for atoms. Like molecules also we can write. Like a species also we can write, any species. Just I'll write for molecules some molecules. Here I'll take one molecule. That molecule is nitrogen molecule, N2 molecule. Now here the N2 means nitrogen combines with the nitrogen, it gives N2 molecule. Atomic number is 7, here also 7. Electronic configuration 1s2, 2s2, 2p3. This is the outermost orbit. Here electrons in 2s2, 2 electrons are paired, but according to Hund's rule in 2p3, here 1 electron, here 1 electron, here 1 electron. These are the unpaired, 3 unpaired, here 1 dot, here 1 dot, here 1 dot. Now here the 2 are they like this. For nitrogen, 1 nitrogen atom, we can write this is the Lewis dot structure for nitrogen atom. Another atom also same thing. Here it is Lewis dot structure for nitrogen atom. Now these two atoms ready to combine, it gives a molecule. While forming molecule, this atom is ready to share to get the octet, a stable electronic configuration. Already they introduced, explained, atom generally has more energy, potential energy than molecule, less stable. They are ready to share to get a molecule, stable molecule. This is a donated one to this. It forms one pair, like pairing takes place. Here it gives like N. It is pair. That pair is formed by 2 atoms. Now this pair is only on nitrogen atom. This pair is only on nitrogen atom. Now these 3 pairs are having equal rights to each nitrogen atom. Now this is equally shared like this. Again it is equally shared like this. This box indicates these 6 electrons are attracted towards nitrogen side and also this side. See here, 2 plus 6, 8 are there. This atom is attains a stable octet electronic configuration. Nitrogen also attains stable octet electronic configuration, becomes stable. Now here the nitrogen and nitrogen, there is a single bond first, then 2 double bonds are formed. Now here 1 paired and here 1 paired. I'll explain afterwards sigma and pi bonds, how it forms sigma and pi bonds. Sir, the Lewis dot structure indicates the number of valence electrons either in atoms or in a molecule. Clear? Like a species also, any species we can write easily. So by using battery prepare like CO2 carbon dioxide, nitrogen dioxide, sulfur dioxide, sulfur trioxide and so on. While writing all these structures, some molecules after forming molecule attains a stable octet electronic configuration, some are not attains. Those who are attain stable octet obey the octet electronic configuration like CH4 like this. For example, here the octet electronic configuration. Here perfect octet electronic configuration is CH4 molecule. Central atom carbon contains its outermost orbit 4 valency electrons because its atomic number is 6. Electronic configuration is 1s2, 2s2, 2p2. In excited state 2s1 and 2p3, here 1 electron and here 3 electrons. In excited state, it is in ground state. This is the ground state electronic configuration. This is the excited state electronic configuration. 4 are there. That's why this is the Lewis dot. Hydrogen atomic number is 1, electronic configuration is 1s1. That's why only 1 dot. Like here, 4 are there. 4 hydrogen atoms ready to combine. It forms 4 bonds. Now this carbon atom, around this carbon atom, 8 electrons are there satisfied. Except hydrogen, remaining all central atom of elements obeys are containing 8 electrons. Such molecules obey the octet principle. See here, hydrogen only contains 2 electrons. 2 electron means that is a duplet electronic configuration, not octet. Except hydrogen, remaining any atom of an element, around the central atom of elements, any hydrogen present which cannot obey the octet, only duplets, but remaining all elements obey the octet electronic configuration if it contains 8 electrons around it. Like some examples we can create. Some are electron deficient molecules are there, do not obey octet electronic configuration. Electron deficient species. They are the limitations of octets. Octet electronic configuration. See here. Here boron trifluoride is there. Boron atomic number is 5. Electronic configuration is 1s2, 2s2, 2p1. In its outermost orbit, only 3 are there. In ground state electronic configuration, here 2 electrons are paired and here 1 electron is unpaired. Whereas in excited state, 2s1 and 2p2, here 1 electron and here 2 electrons are there. That's why for this Lewis dot structure is, we can write like this for boron atom. Now in boron trifluoride, another atom is fluorine. Fluorine atomic number we know 9 and its electronic configuration is 1s2, 2s2, 2p5. Now this is the outermost orbit. Here 2 are paired and here out of 5, 2 pair and 1 is unpaired. That's why for fluorine, here it is paired, now it is paired, now it is paired, now on single dot. This is the Lewis dot structure for fluorine. Not only fluorine, like chlorine, bromine, iodine and astatine, all are denoted by X halogens, that is denoted as X. Here are 3 pairs and 1 is unpaired. Around boron, here around boron 3 fluorine atoms are there like this, 3 fluorine atoms. Now each fluorine atom contains 7 valence electrons. Out of 7, 1 is unpaired, remaining 3 are the paired. Like, sorry, I'll take here. Now here this fluorine atom donate 1 electron to this, boron also donate 1 electron to this, it forms a 1 electron pair. Same similarly here 1 electron pair. Same similarly here 1 electron pair. Around boron, after sharing equally by fluorine and boron, around boron only 3 pairs are present. It contains only 6 electrons. If it contains 8 electrons, like here are 2 like 8 electrons, this is 8 electron, obey octet electronic configuration. But here around boron, how many are there here? 6. Do not obey octet electronic configuration. So here do not obey octet electronic configuration. This is a electron deficient molecule. And in boron, one vacant orbital is there. Here it contains one vacant orbital. That's why it is ready to receive the electron pair. In equilibrium, electron pair donor, electron pair acceptor. Lewis acid-base theory is there. Electron deficient species. It acts as an electrophile. And it is acts as a Lewis acid. But here fluorine obeys 8 electrons. Each fluorine obeys 8 electrons. But total molecule do not obey. Central atom do not obey octet electronic configuration. It is electron deficient species do not obey octet electronic configuration. One more is super octet electronic configuration is there. Super octet electronic configuration means central atom of an element contain more than 8 electrons. Just like here boron trifluoride, I will take SF6. Sulfur atomic number is 16. Electronic configuration we know, that is neon 10. And here 3s2 and 3p4 electronic configuration. Sulfur 16. So by using this, here it contains total around this sulfur total here 2 electrons, and here pair is like this. Pairs, 2 pairs are there, 2 are there. Here 2 are these out of 6 electrons, just like oxygen. I'll take oxygen. Here 1s2, 2s2 and 2p4. Outermost orbit. This is outermost orbit. Here 2 electrons, and here 2 are the unpaired. That is 2 are pairs are present, remaining 2 are the unpaired. Just like here sulfur also like this, but here around sulfur 6 fluorine atoms are there. To get the bond, 6 unpairs required. That's why this electron is excited from 3p to 3d, and this electron also excited from 3s to 3d. 2 excites takes place, first and second excites. After that, here we'll get 1, 2, 3, 4, 5, 6. These are entered into the d orbitals. D subshell. Here total sp3 d2 hybridization I'll explain. Total around these sulfur. Here 6 valency electrons are there in excited state. Second excited state. In second excited state around sulfur, total 6 valency electrons are present. 1, 2, 3, 4, 5, and here 1 more, 6. And here the 6 fluorine atoms are present. 6 fluorine atoms. Each fluorine atom donate 1 electron, like 1 electron. It forms 6 covalent bonds around this sulfur. 1, 2, 3, 4, 5, 6 pairs are there. 12 electrons are present. These are more than 8 electrons. More than 8 electrons means it is a super octet electronic configuration. Just I am giving one example. In your material synopsis, so many examples are there based on this. But here fluorine obeys 8 electrons. Already 3 pairs are there, 1 is. Like SF6, here the PCl5, IF7 are the examples for super octet electronic configuration. Some are obeys exactly 8 electrons. Some are do not obeys. Which do not obey octet, they are called the limitations of octet. They are the electron deficient, electron efficient. Some are odd number of electron species are present, which are also not obey octet. Are like NO and NO2 are the best examples. So final conclusion is, by using Lewis dots, we can represent the number of valency electrons. We know the valency electrons, we can easily represent the number of dots. We can identify easily number of dots. By using number of dots, we can easily identify the valency. What is valency? Here valency. Valency means here the combining capacity. Combining capacity of an element, that is called valency of an valency and oxidation state. Here the oxidation state and valency or oxidation number in first year. Unit number redox reaction, we know this information about this valency and oxidation states. Here valency is the combining capacity of an element. Generally, your combining capacity is generally group number. Generally, group number applicable, it's valency, but it is not applicable for all groups. Here, generally, valency is 8 minus group number. 8 minus group number. By using this formula, we can calculate its valency. That is from your 14th group onwards. For example, your carbon family or 14th group, your 8 minus its group number is 4. We can take its valency is 4. For 15th group, your 8 minus 5 group number, that is 3. Your 16th group valency is 8 minus 6, that is 2. Combining capacity. 17th group halogens 8 minus 7, that is only 1 valency. 18th group, 0 group, that is valency is 0. 8 minus 8 is equals to 0. So its combining capacity is 0, means exist as monoatomic gases, all noble gases, because there is no combining capacity. Like helium and helium, there is no bond, there is no combining. A weak van der Waals force exists between. Or here the neon and neon, there is no attractive forces. Weak, there is no strong attractive. There is no particular force. There is no combining capacity. Just weak van der Waals forces exist. This is the valency, easy to calculate by using Lewis dot structures. By using all these, here in this combining capacity, electrovalency is there, electrovalency, and here the covalency is there. Here the electrovalency is nothing but number of electrons transfer. Number of electron transfer from one atom to the another atom. But here the covalency means number of electrons shared between two same or different atoms. How it shares, I will explain right now. Okay, so are the electrovalency and covalency. Best example is NaCl is there. The electrovalency of Na is equals to 1. And here the electrovalency of Cl is also 1. Because from here, sodium to chlorine, how many electron transfer means? Only 1 electron. That is the combining capacity. For example, here the O2 molecule is there. Here oxygen and oxygen, there exist even double bonds. Between oxygen and oxygen, how many bonds are there? Two bonds are there. So each oxygen atom, how many electrons donated to the another oxygen atom? Two electrons. How many electrons are shared here? Two electrons are shared. That's why sharing, while using in a sharing nature, we can use the word covalency by transforming electrons from generally metals to the non-metal. I'll explain the story about how it transfers. That is electrovalency and covalency of the atom of an elements. Now, mode of chemical bonding are the types of chemical bonds. With the help of Lewis dot structure, octet electronic configurations, and valency and oxidation states, and atom and molecule existence, are the mode of chemical bonding. In this mode of chemical bonding are the type of CB chemical bonding or mode of CB chemical bonding. So based on their attractive forces between two atom of an elements are the two things or two substances in a system, based on the type of things participated in a process, different types of forces or attractions are exist. Generally, between a student and a lecturer, there is a good rapport, good relation, good attraction. That is a student and lecturer attraction. That is one type of force. Between parents and children, there exists a good rapport, good attraction, parents and children attraction. Between different parents and respective children, there exists a respective attraction. Based on their affection, love and affection, there exists a good attraction. Similarly, based on the type of atoms or molecule participated in a chemical reaction, different forces exist. Here, different forces are covalent of force, and here the electrovalent force, along with the covalent and electrovalent force, coordinate force, here metallic force are the attraction. Fifth one is van der Waals force. So different types of van der Waals forces are there in gaseous state. Will explain it there. Generally, here to get the covalent force, two atoms must be generally electronegative and electronegative elements. Generally, it forms this type of covalent forces. So what is electronegativity or electronegative elements means are the elements which have the capacity to attract the shared pair of electrons towards itself. That is called a electronegativity. Here generally electrovalent force exists between electropositive and electronegative, different. Here coordinate covalent is the type of covalent force only generally. Now here the metallic force means generally exists between electropositive and electropositive only, between two same type metals and metals alike. Here van der Waals forces are generally between molecules, so weak van der Waals forces exist. Now I'll discuss about covalent force, covalent bond, types of covalent bonds, factors which influence the covalent bond, and some important characteristics of covalent bond. In 2019, one question given based on this. Guarantee 3 questions we can expect every year. 2019 3 and previous years also regularly 3-4 questions are asking. Next year for our batch also in 2020 they'll ask guaranteed 3 questions from 3 different areas. They'll ask This is the one area to ask one question. Last year asked one question, that is, it was based on one compound given. This compound is covalent in nature or metallic in nature or ionic in nature, like a combination one question created. While explaining the problems, I'll show this model. Clear? Sir, what is a covalent bond or the covalent force means? Generally, a bond is formed by mutual contribution and mutual sharing. Now, this is A, one atom, another atom is A. Your A atom donate one electron to the another A atom, it forms one electron pair. That is called a mutual contribution and mutual sharing. A donate one electron to another A, then between A and A, it forms one electron pair. That is called mutual contribution and mutual sharing. To get a bond between A and A, like A bond like this, A bond A, one single bond, single covalent bond, A must donate one electron to another A. This A also donate one electron to this first A, then it forms one electron pair that is equally shared. One electron pair is equally shared, one single bond is formed. Now, two electron pair shared, two bonds are formed. If three electrons are shared, three bonds are formed. Your B and B between two electrons are shared like this, then it forms your B and B between these two electron pairs are shared. Your two bonds are formed, your B bond B, sigma and pi bond. Similarly, between C and C, three electron pairs are shared. It forms a three covalent bonds. One is sigma, remaining two are the pi bonds. These are called a multiple bonds. More than one bond is present. And once we can observe all these examples, your same atoms are present, either single or the multiple bonds. That's why these examples are generally called a homoatomic. Homoatomic, heteroatomic. Homoatomic means same type of atoms. Like your hydrogen and hydrogen, H2 is a homoatomic. Like Cl plus Cl, it gives Cl2, homoatomic. Here, how many atoms are there here? Two atoms are present. That's why we can use homo diatomic. Homo diatomic it is. Like oxygen and oxygen, it gives O2, homo diatomic, but here double bond is present. Here nitrogen plus nitrogen, it gives N2, triple bond is present. They are homo diatomic. Some are here heteroatomic are there. Heteroatomic molecules means here the A and B different. Like H and Cl, like H and oxygen, hetero, different atom of an elements, equal contribution takes place, it gives the corresponding bond. That is mutual contribution, mutual sharing takes place. And your electronegativity difference between these, electronegativity difference is less than 1.7. Experimentally determined in a chemical bonding in a periodic table based on their Pauling scale and a Millikan scale to calculate the electronegativity. Electronegativity difference is less than 1.7 between such molecule. There exists a covalent bond. Again, here based on this, based on the type of atoms, homo and hetero, your covalent forces are again two types are there. There one is polar covalent and non-polar covalent. Polar and non-polar covalent molecules are there. Tomorrow I'll discuss about polar and non-polar covalent molecules and some important conditions to form covalent force and some important characteristics. In this unit particularly, better you concentrate on all synapses. Based on all the synapses only, they'll ask very simple, silly questions. From these types of chemical bonds or the mode of chemical forces, guarantee we can expect one question, which is covalent or ionic. There is an important Fuzzen's rule is that tomorrow we'll discuss. We'll finish this. Maximum chemical bonding is divided into 4 areas. Introduction and like this. Here, Vesper theory and VB theory, one area. Hybridization concept is one. Then molecular orbital theory is one. Okay? Tomorrow we'll discuss.